bumping lemma is fun. We're trying to prove that certain languages cannot be done by a regular language, right? So here, for example, 0 to the n, 1 to the n, that's right, A star, B star is the number of A's and the number of B followed by a number of B's, but there's not a link between them. But here, 0 to the n, 1 to the n, you can have any number of zeros as you want, but then you have to have the same number of ones. And the DFA, of course, how does it solve that? Well, it has to count the number of ones. And to count up to 7, you need 7 states. To count to an arbitrary number, then that's more problematic, right? So, I had these slides which talked about, what do you know in a state, right? And what does anyway, in this state, we're saying what you know is all the strings that arrive there, right? And so now let's talk about the idea of a language distinguishing two states, right? So distinguishing two strings. So the string 0, 0 and the string 1, 1, well, the machine doesn't distinguish them. The machine 0, 0 goes here and 1, 1 goes here. So the machine doesn't distinguish them. But let's see what it means for the language to distinguish them, right? The language, we say the language distinguishes them if there is some, now this is a zeta, right? So alpha and beta are the beginning of the alphabet. So they're the beginning of the string, and zeta is the end of the string. If maybe the language doesn't care whether, gives the same answer to 0, 0 and 1, 1. But if there's some zeta such that alpha zeta and beta zeta have different answers, then we're going to say they're distinguish them. But in this case, if the answer so far, if what we've read so far is 0, 0, 1, 1, then the language says, well, the language cares about how many characters there are. Well, those two strings have the same number of characters, so it doesn't care about that. And the language cares about whether the number of ones is even or odd. Well, here with 0, 0, the number of ones is 0, which is even. And with 1, 1, the number of ones is 2, which is even, right? So it doesn't care between those two strings. So, right, on the other hand, 0, 0 and 0, 1, they are distinguished, right? So because there's a future which cares the difference between them. All right, so anyway, let's go on to what we're doing here. Oh, I gotta admit some people still. All right. So the standard proof to prove that this language can't be done by a DFA is called the pumping lemma. And I find it very complicated. It has 5 levels of alternation. If for alls exist, it alternates a statement that alternates between for alls and exist. And if you're taking 1090, you know that having 5 levels of alternation is confusing, right? So the very first term I was teaching this course, I started at York in 95 before you guys were probably even born. I said, hey, I don't want to teach the pumping lemma. So I made up my own theorem, and out of a joke, I called it the bumping lemma. All right, and Eric Rupert, who's in the office next to me, and I talked about and proved some things about the bumping lemma, and I think it's better. So later, somebody told me that actually I didn't invent the bumping lemma. Some guy in 58 invented it. But, you know, it's more fun to invent your own theorems than to read up and see what other people do. So let's try to understand this thing. All right. So here's a language. All right. And this language is just going to be a set of names, right? Jeff Edmonds is in the language. Jeff Rupert's in the language. Super Cash Edmonds is in the language, right? Those are very strings that are in the language. So if the machine inputs one of those, the machine needs to say yes, right? And if the machine there are other things that are not there, right? So let's see, Jeff Data, right, is missing. So if the input's Jeff Data, the machine should say no. All right, so here I just formed a little bipartite graph. There's a first name and a last name, and I put an edge between them if it's a good name. And so there's an edge here. Jeff Edmonds is a name, but Jeff Data, I don't have an edge there, right? So Jeff Data is not a good name. Right? So what is the DFA going to do? It's going to read in this name, and at some point it reads the first name, right? And the question is, does it have to remember the entire first name, or could it remember some lesser information? And why does it remember the first name? Is because later it's going to read the last name, and we have to see, does the first name, last name, is that part of the language or not? All right? So that's what I just said. When you read the first name, what do you have to remember? Do you have to remember the full first name, right? How many states do you have to have? If I want to remember Jeff, Supercash, Data, or Patrick, then I'm going to need 4 states, right? One state will remember that I'm in Jeff. One state will remember that I've read Supercash at Patrick or Eric. These are all, by the way, professors. The diagonal here, Jeff Edmonds, Supercash Data, Eric Rupert, and Patrick Diamond are all professors in theory at York. All right? So we might need a different state for every first name. All right, so here's my machine. And you know my machine reads one character at a time. But so here I'm starting, and then somehow I read one character at a time. And then after reading the first name, what state am I going to be? So here, as I said, I have a state for each of the first 3 names. And then when do we accept? Well, you have to read the last name, right? So here, if you're a Jeff and you read Edmonds or Rupert, then you're going to accept. If you're at Supercash and you read Edmonds, Data, or Rupert, then you're going to accept, right? So everybody see here, this is what a DFA kind of looks like, right? Any questions about that? Right. And so now everybody study this and see, do we need all these states, or is it okay to have fewer states? Can you delete one of the states? Right? What about Edmonds versus Supercash? Well, Jeff versus Supercash. Well, the reason you have to remember is because if it's Jeff and Data, then the answer is no. But if it's Supercash and Data, the answer is yes. So you have to distinguish between Jeff and Supercash. But what about Jeff and Eric? Well, I mean, Supercash and Eric. Supercash, you say yes for Edmonds, Data, and Rupert. And Eric, you say yes for Edmonds, Data, and Rupert, right? So it doesn't matter. Their futures are the same, right? So these 2 guys here, the language doesn't distinguish between Supercash and Eric because their future no matter what you get in the future, well, the future depends on what you get in the future, but it's the same independent of whether you've read Super Cash or Eric so far, right? So here we've made the DFA smaller, right? So what's our new DFA? You read the first name, and if it's Jeff, you go there. If it's Patrick, you go here. But in Super Cash or Eric, it doesn't matter. You can end up in the same state, right? And then when you read the last name, it determines whether to accept or not. Everybody see how this DFA is good enough?
Yes.
All right. Fewer states, right? So this language, who's going to invite to the party, distinguishes between Jeff and Supercash because here, why does it distinguish between Jeff and Supercash? As I said, because there's a future, right? If Jeff is alpha and Supercash is beta, then there exists a zeta data such that Jeff data is not invited, but beta zeta, right? Alpha zeta is invited and beta zeta is not invited, meaning Jeff data, right? Does that make sense? That's why they're distinguished. So because they're distinguished, they need to be in different states. All right, so I've done a number of papers on communication complexity, which means how many bits, if I want to communicate to you and I are going to solve some problem together, and we want to know how many bits of information do I have to communicate in order to solve the problem. So here the problem's going to be, there's two boys and they look like twins. The first guy knows the first name and the second guy knows the second name. All right. So, and together they have to decide whether the name is a good name, right? If it's Jeff Edmonds, they say yes. If it's Jeff Data, they want to say no. But one knows the first name and one knows the second name. And the game is the first guy sends a message to the second guy, right? And the question, we're not doing bits complexity here. We're doing how many distinct messages, right? So how many distinct messages must he send, right? So that he knows whether or not the person is invited. And I'm claiming he could send one message. If it's Jeff, if his first name's Jeff, he could send the message Q1. And if the first name is Supercash or Eric, he could communicate the message Q2. And if the first name is Patrick, he can send the message Q3, right? Why is that? Well, because then the second guy knows what the answer is, right? So you might say these messages are in fact the states. And how the first half, how the DFA, the part of the DFA that reads the first half of the message communicates to the second half. It communicates it via which state it's on in the middle, right? So the first half of the machine reads the first name, and based on the first name, it'll be in one of these three states. And that's how it communicates to the second half of the machine that reads the second half of the name, right? Does that make sense? Right? Right? Because Jeff and Supercash have different possible, the future depends on whether it's Jeff or Supercash, right? For Jeff Data, right? I don't invite them, but if it's Supercash Data, then the second guy does invite them, right? So the second guy needs to know whether it's Jeff or Supercash, right? So that's why the first guy sends a different message with Jeff and with Supercash, right? But Supercash and Data are not distinguished, so we can send one message, right? Everybody kind of following that? So this is what we said before. We say a language L distinguishes alpha and beta if there exists a zeta such that alpha zeta and beta zeta have different answers, all right? And in this case, Jeff Data and Supercash Data have different answers, and hence the language distinguishes between Jeff and Supercash. Right? All right. Now, we want to get a whole set of strings that are distinguished by our language. All right? Here's a set of first names. Jeff, Supercash, and Patrick are three first names, and each pair of them is distinguished, right? We know that Jeff and Supercash were distinguished by the last name Eric. Maybe Jeff and Patrick are distinguished by a different string, and Supercash and Patrick are distinguished by a future zeta, right? Each pair might have a different zeta, but each pair are distinguished, right? Then this is what the bumping lemma is going to say, right? If I have a set S of strings such that every pair is distinguished, then any DFA that solves the problem needs to have the number of states has to be at least the size of this set of strings. Why is that? Because Jeff and Supercash need to go into different states, and Patrick needs to be in a third state. That means if you're going to solve this, you need at least 3 states, right? Maybe more than 3 states, but at least 3, right? So what we're saying is no DFA that has fewer than S states can solve the problem, right? Does that make sense? And why is that? Well, here's an example of a DFA that does have at least 3 states, right? It actually has more than 3 states, but it has at least 3 states and it solves the problem, right? So now, I don't know if somewhere, remember we have short versions of the slides and long versions of the slides, right? So certainly in the long versions, I prove this theorem, but maybe in the short version, I don't prove it. So let's, for the moment, at least assume that this theorem is true, right? Then how are we going to use the theorem to prove that 0 to the n, 1 to the n cannot be solved by any DFA, right? Well, the language L, what is it? It consists of a block of zeros followed by a block of ones, where the number of zeros and the number of ones have to be the same, right? So you can think about, you have to take this string and break it up into first name, last name. And the clear first name is 0 to the n, right? And the clear last name is 1 to the n. So think about it as the first boy knows how many zeros there are. And the second boy knows how many ones there are. And what does the first boy have to tell the second boy? He has to tell him how many zeros are there, right? The first boy has the number of zeros. So he says, how many boys are there? And he has to say how many zeros there are. And how many states does that require? Well, there are an infinite number of possible numbers of zeros, right? So you need an infinite number of states, right? So here, let's do it. Suppose, this is what I said. Suppose I read the first name as being, I got 3 zeros. Or I read the first name being 4 zeros, right? Do I need to distinguish between whether there were 3 zeros or 4 zeros, right? Suppose I went to the same state, right? After reading 3 zeros, I go to some state. And after 4 zeros, I go to the same state. Suppose I don't tell you whether there are 3 zeros or 4 zeros, right? But the problem is that the language requires me to differentiate between these. Why? It's because suppose the last name was 3 zeros, right? Then had my first name be 3 zeros, then alpha zeta would be 3 zeros, 3 ones, right? And the answer would be yes, because the number of zeros equals the number of ones, right? But if my first name had been 4 zeros and then I read the last name with 3 zeros, then it would be 4 zeros, 3 zeros, and the answer would be no, right? So I need to be able to distinguish between 3 zeros and 4 zeros because the future requires me to know the difference, right? Does that make sense? Right? So that means any DFA that solves this language must put 3 zeros and 4 zeros into different states, right? All right, that's great. Now, but we're going to find an infinite number of such first names, an infinite number such that each pair needs to be distinguished, right? And if each pair needs to be distinguished, then each of these infinite number of first names need to go to a different state. And hence I need an infinite number of states. And hence no finite automata can solve the problem, right? Oh, so here we do it with the boys, like I said, right? The first boy gets some number of zeros. The second boy gets some number of ones. And the first boy sends a message, right? And then the second boy has to know, were they the same number or were they different numbers? Well, what does the first boy have to do, right? For every number of zeros, he has to send a different message, right? And why does he have to send a different message? Because the second boy needs to know how many zeros there were, so he knows whether or not it's the same. And hence, there has to be an infinite number of messages, right? This is, again, we're saying 3 zeros and 4 zeros are distinguished, right? If he sends the same message for 3 zeros and 4 zeros, then the second guy won't know what to do when he has 3 zeros, 3 ones, I mean. All right? They had to be given different signals. All right, so I guess here is kind of the proof we're talking about. Here's a machine with a bunch of states, right? And we're giving you these states for free. Here's some other states. And what we're going to do is for each string, the first name is some number of zeros, right? Run this machine on 1 0 and on 2 zeros and on 3 zeros, right? And where do you go? Well, maybe 1 0 takes you to that state. Maybe 2 zeros takes you to that state. 3 zeros to that one, right? So now there's an infinite number of possible numbers of zeros, right? Infinite number. You can have 1, 0, 2, 3, 4, 5, 6, 7 up to infinity. An infinite number of possible strings, right? But this is a finite automata. So because there are only a finite number of strings here, states here, that means there must be some state that gets 2 of the same first names, right? Say this state gets 3 zeros and gets 4 zeros. If you run this machine on 3 zeros, you end up here. And if you run it on 4 zeros, you end up here as well, right? Then what do you know? Well, suppose our future is we get 3 ones. Well, here, if I got 3 zeros and 3 ones, then I better accept, right? If I get 4 zeros and 3 ones, I better reject, right? But our machine here is going to give the same answer, whether it's 3 zeros, 4 1, 3 zeros, 3 ones, 4 zeros, 3 ones. The machine's going to give the same answer, right? So one of those answers has got to be wrong, right? The machine distinguishes between these. One's in the language and one's not in the language, right? Hence, these different first names should go to different states or your machine doesn't work, right? So you need an infinite number of states. Does that make sense? Right? Everybody good?
Just to be clear, you use like almost like three ways to show it. They're not like a continuation. It's like three different ways to show it.
You mean like the boys versus the this versus the that?
Yeah.
Those are just intuitions,
Oh,
right? I'm just trying to get you to understand it. What do you need to know? You need to know the bumping lemma, right? I'm not going to make you prove the bumping lemma. We could prove it if you want, but we sort of half proved it already. The bumping lemma says, suppose you have a set S that could be finite or could be infinite, and each pair is distinguished, right? Each pair of strings, for each alpha and beta in the set S, there's a zeta such that alpha zeta and beta zeta have different answers, right? Then it follows that any DFA that solves it needs at least S states, right? So you need to understand what this means, and then you need to use it.
okay.
Do you understand what this means, do you think?
Yes.
All right. So in the past, I had lots and lots and lots of really hard examples. But now we're doing Reader's Digest. We're going to do one or two easy examples. Oh, in fact, what I did in the past was I taught you a bunch of hard examples, and then I gave you a really hard example on the test and a real hard example on the exam, right? But now we're going to give you easy examples on right now, and then on the test, you are going to have to do this on the test, but I'm going to give you an easier example. All right? So, right? So here, I'm just, I love first order logic, right? So here, let's practice our first order logic again, right? This is saying, if there exists a DFA with fewer, here M, the size of M, here the DFA is M, so the size of M is the number of states, right? The number of states is less than or equal to the number of strings in our set S, right? We're trying to say a DFA with fewer, that there is a DFA with fewer states, right? Here I'm saying there exists a DFA since the number of states is less than S. And what does this DFA have to do? Well, in every input, it has to give me the right answer for the language, right? So you can see this is a nice finite state. This is a nice logic statement, and you should be able to read it and understand it because you're all experts at 1090, right? The point is there exists one DFA that works for every input, right? The problem L does not have a DFA, right? Here we're saying L does have a DFA with fewer states. Now we're taking the negation of it. We're saying it doesn't have, right? So to say it doesn't have, we're saying for every DFA you could give me, if it has fewer states, then there exists an input on which it gives the wrong answer, right? Does that make sense? So the game, if you like 1090 games, is you give me any DFA whatsoever, right? That has any DFA that has fewer than this many states, right? Then I'm going to come up with an input and prove to you that the input, your DFA on that input gives me the wrong answer, right? Does that make sense? Right? We're saying for every DFA, there's an input in which it gives the wrong answer. So that's what our bumping limit says, right? Right. So now I'm going to give you a proof of this, right? And how do we do this proof? Well, if you took 1090 from me, you know we're going to follow the game, right? So how does the game work? Right? Those of you who are not in 1090, the game is you read from left to right. And if it's an exist object, then the prover comes up with it. And if it's a for all object, then the adversary comes up with it. All right? So let's play the game. It starts with for all DFAs. All right? So the adversary gives me some DFA that has fewer than S states. Right? And then I have to come up with an input. And then I win if your machine gives the wrong answer for this language for my input. Right? Everybody understand the game?
What is the M there?
The M is the DFA machine.
Okay.
Right? We want to prove that every DFA M, where M has fewer states. Right? If you give me any DFA that has fewer states than the size of the set S, then I can come up with an input such that your machine on that input, your DFA on that input, isn't the required answer for my language. Right? Does that make sense? Right? So how are we going to do it? Right? Remember what S is. S is a set of strings which each pair are distinguished. Right? So the adversary gives me a deterministic finite automata, M, that has fewer than the size of S states. So here is a machine, right? I just kind of drew a picture of it. We don't really know what his machine is, but it has a bunch of states and it has a bunch of edges between them, right? And I need to come up with an input in which his machine doesn't work, right? So how am I going to do that? Well, I've said that every input, it can be broken up into an alpha and a beta, an alpha and a zeta, right? First name, last name. Every string in my language, I've broken into alpha and zeta. And S is a set of alphas, right? Alpha or betas, right? So S is a set of them. So I'm going to take every string that's an S, and I'm going to start at the start state, and I'm going to run the machine and see where it lands, right? So I run it on alpha 1, and I land in that state. I run in alpha 2, and I run on that state. I run in alpha 3, and I ended up on that state, right? Each of my first names that I have in my set S, I run the machine, and I see which state it lands in, right? Now, that was great, but we know that the total number of states is fewer than the total number of strings, right? Do you know that there's a thing called the pigeonhole principle? And the pigeonhole principle says if I have more pigeons than holes, and all the pigeons fly into holes, then there's some hole that has 2 pigeons, right? So that's what we're saying here. I have more strings than states, and each string goes into one of these states. So what do we know? There must be some state that has 2 different strings go to them, right? Everybody follow that? So I'm going to call the strings alpha and beta. Alpha and beta are both in my set S, and they both go to the same state, right? Everybody buy that? So now what happens, right? Well, look at, by the definition, right? We said every pair of strings in S are distinguished. And what's the definition of distinguished? Is up here, right? Because they're distinguished, alpha and beta are in S, hence they're distinguished by the language. Hence there exists some zeta such that alpha zeta and beta zeta have different answers, right? One of them, the machine's going to say yes, and one of them is going to say no. Maybe we don't know which is which, but one's yes and one's no, right? So let's start at this state and run zeta, right? So here, all we know is that alpha zeta and beta zeta have different answers in the language, right? We don't know what that answer is, but it's one's yes and one's no. All right, so we start at this state, and our goal is to prove that the machine gives the same answer on alpha zeta as beta zeta, right? I'm going to say your machine, here's your machine, it gives the same answer on alpha zeta and beta zeta. Why? Because you start at the start state, you read alpha zeta, you end up somewhere. You start reading beta, you get to the same state. Now, from this state, reading zeta gets you somewhere, right? So from here, it's a deterministic machine. So if I start here and I read some zeta, right, I'm going to get to some state. Maybe it's this state. Suppose I read zeta, I get to this state. Well, then that means alpha zeta is going to get to this state, and beta zeta is going to get to the state. So that means the machine is giving the same answer to alpha zeta and to beta zeta, right? But we know that the language gives a different answer to alpha zeta and beta zeta, right? Everybody follow that? Now, look at what we have here. Do both of these have the right answer? Can this machine give the right answer to this string and give the right answer to this string? No, right? It can't, right? Either the machine gives the wrong answer for alpha zeta, or it gives the wrong answer to beta zeta, right? If one of them's right, then the other one's wrong, right? And so my goal is to produce an input in which the machine gives the wrong answer. And I claim it either gives the wrong answer on alpha zeta, or it gives the wrong answer on beta zeta. And we have finished the proof. Right? Isn't that nice? Everybody see how we use the little 1090 in here? And we managed to come up with the proof. And you can see why I wanted to teach 1090, because people are having a hard time with this kind of proof. And so now people who are taking 1090 should be able to do this kind of proof. Anybody want to say anything? Are you good? All right. So what I gave this proof technique to Eric. You probably have all seen him. His office is next door to mine. A very sweet man. He's actually now our boss. He's not the boss anymore. He was the boss last year. He was the undergrad coordinator. Now Supercash Data is the undergrad coordinator. So anyway, he then proved something else. He proved the opposite. He proved that if S is the maximal set of pairs that are distinguished, right? It's the biggest set you can possibly form of distinguished strings. Then he gave an algorithm for building a DFA with this many states. So what I proved is that build the biggest set for your language. And I proved that no DFA can solve it with fewer states. And he proved that there is a DFA that can solve it with the exact right number of states. So this idea of coming up with the set of strings that are distinguished by the language, it completely characterizes the size of the smallest DFA, right? And the proof's not so hard, but we're not going to cover it. All right, everybody got that? So now, once you have that proof, of the bumping lemma, right? Now, how do you prove that 0 to the n, 1 to the n has no finite automata? What you do is you give an infinitely large set that's are distinguished, right? 0 to the n, 1 to the n are distinguished, right? Right. So now let's go to our set S and how we can prove that it works. All right. So here, what does this say in logic? It says if there exists an infinite set of strings S, right? So if there exists a set of strings such that for every pair of strings, you give me any string, alpha, beta, in S. Now, of course, there better be different strings. If alpha equals beta, then that's not very interesting. You give me two different strings, then I'm going to prove to you that there exists a zeta such that alpha zeta and beta zeta have different answers in our language, right? That makes sense? And what we proved up here is that if this is true, then this is true, right? In fact, you might say, how did I prove this, right? I assume this, so I used this as an oracle, right? How did I use this in an oracle in the proof? Well, I was cranking around, right? The oracle promised me that there was some set S. And then I took this set S and I ran each string through this machine. And when I ran it through this machine, that gave me an alpha and a beta, right? And then I went back to the oracle and I said, here, I gave the oracle alpha and beta, right? And what did the oracle do? The oracle gave me a zeta, right? So I use this just as an oracle we do with an oracle. Does that make sense? There, we just gave you, people who are taking 1090, we just gave you another example of an oracle test, an oracle proof, right? All right, so now let's do this. Here's our language. And we want to prove that there exists an infinite set such that every pair that are different has a zeta, right? And if we do that, then we know that there's no DFA for it. How do we prove it? Well, the first guy, it exists in S, right? So the prover has to come up with a set of first names, right? And the first, we know all strings that we care about, all strings of the form 0 to the n, 1 to the m for possibly different n and m, right? So what's our first name going to be? Well, it seems obvious our first name should be the zeros, right? So now what am I going to let my set S be? I have to come up with a set S. Well, it'll be all strings of zeros, any number of zeros. We can have 0, 0, 1, 2, 3, 4, 5, any number of zeros, right? Is this an infinite set? Yeah, because n has an infinite number of possibilities. So S is an infinite set. So I just came up with an infinite set, right? Now, that's how we're proving this, by the prover coming up with the exists. Now, the adversary, it's the adversary's turn now, right? The adversary is going to come up with the for all. The adversary is going to say, let alpha and beta be arbitrary, right? That's my set S. Alpha and beta means that the adversary gets to choose two strings, has to choose two strings from S, right? So I've told everybody what S is, and then the adversary comes up with two strings. And we say, well, let alpha and beta be arbitrary strings from S, right? We know they're from S, so we know that that they're a string of zeros, right? So let's say alpha is the string with I zeros, and beta is the string with J zeros. And we know that they're different, so we know that I doesn't equal J, right? So what is the adversary giving me? it's giving me I zeros for my alpha and J zeros for my beta, right? All right, so that's what we have there. And now it's an exists zeta, right? So it's now my job to distinguish I zeros from J zeros, right? I have to come up with some last name such that alpha zeta and beta zeta have different answers in the language, right? And what's my language? Some number of zeros followed by some number of ones, right? The same number of ones, right? So that exists zeta, it means I get to choose zeta, and I get to choose any zeta I want. Well, my zeta is going to be some number of ones, right? And which zeta do I want? Well, what I want is for alpha zeta to be a yes, and I want beta zeta to be no, or vice versa, right? So how do I get a yes here? How is alpha zeta a yes? How is 0i 1k a yes? Well, it's a yes when I equals k, right? That's how I get a yes. So what am I going to do? I'm going to let my zeta be I ones, right? The oracle, the adversary gave me I zeros and J zeros. So I'm going to let my zeta, and then that gives me that alpha zeta is I zeros followed by I ones, and that's a yes of the language. But beta zeta is J zeros followed by I ones, and I and J are different, so that's a no, right? Does that make sense? And then I win the game. That's how I prove that this is true, right?
Why is that?
So what are you going to have to do on the test? Guaranteed, this is going to be on the test. I'm going to give you some language like this. And what are you going to do? Your goal is to prove that no DFA can solve it. How are you going to do it? You're going to come up with some infinite set of first names, and then the adversary is going to choose some two of them from your set, and then now you know alpha and beta, and you knowing alpha beta, you get to come up with some zeta. And then you prove that alpha zeta and beta zeta have different names, different answers. Right? Does that make sense?
So basically, we are
Everybody
playing
good?
games again.
Could
We are
you
playing
explain?
games. Like,
Yeah, guys. You thought you're getting out of 1090, but no. No. I'm
Ah,
all about playing these games.
okay.
Could you re-explain the L alpha zeta part again? The second square. Yeah, that part.
Second square. The alpha and beta?
No, it's the from the bottom.
Well,
So the L alpha
one?
zeta. Yeah, that one.
right. So I come up with the set S. The adversary comes up with an alpha and beta. I come up with the zeta, right? And what I need to do is I need to study the adversary's alpha and beta. And I want to say, why do I care, right? If this is my first name or this is my first name, why do I care which it is? What I care is because what future could make alpha zeta a yes? All right, so I could focus on that. How do I make alpha zeta a yes? Give me a zeta which makes alpha zeta a yes. All right, well, if it's the same number of zeros followed by the same number of ones is a yes, then if I have I zeros, I need I ones to make a yes, right? So I'm going to make zeta be I ones. That's right. I just got to make it whatever I want. And then, well, alpha zeta is a yes. Why? Because it's a yes because I made it that way, right? That's why I chose zeta, to make it a yes. Well, let's see if I was lucky. let's check. Does beta zeta, is beta zeta a yes? Well, beta zeta is J zeros followed by I zeros. And we know I and J are different. So is that a yes? No, that's a no.
So if you pick the zeta as 1J,
Yes.
it's going to change the term,
Yes.
right?
Right.
Okay.
Right? That's just as good. Right? That would have been just as good.
Okay.
No, but if I made it be hello, right? Maybe zeta is a hello. Then alpha hello, well, that's the no. And beta's hello is a no, right? So hello doesn't distinguish between them, right? So sometimes it takes if it's a hard example, it's hard to come up with S, and then it's hard to come up with zeta, right? But hopefully I'll give you an example that's easy. And for easy examples, it's easy. Hopefully it's easy, right? Right? And then once you've done this, then you could say, hence, right? Now you want to finish the proof. Hence you say, hence L is distinguishes our set S, and hence any DFA computing L needs at least an infinite number of states, right? Hence no deterministic finite automata can compute L, right? That's how you finish. And that's what you have to do in the test. All right? Everybody understand that? So let's do another one. All right? If you, as I say, if you go to the long version, I do like 8 of them, and they get harder and harder and harder. But we don't want to do really hard ones. So I don't remember how many we do here, but let's do another one. So here, what's our language? Any number of zeros followed by any number of ones. But now the number of zeros has to be greater or equal to the number of ones, right? It just has to be longer, right? Everybody understand what the language is? So how do I do it? I have to come up with the set S. Well, the set S we had before was pretty nice. Let's do it again. Let's just have this first names are being just zeros. And so I claim any number of zeros are going to be distinguished, right? So the first name is just some number of zeros. And then what's our adversary going to do? Our adversary is going to choose 2 strings, alpha and beta, that are from S, right? And only requirement is that they're different. So what does he have to give us? He has to give us some I zeros followed by or some J and some J zeros where I and J are different, right? So he gives me this string and this string, right? Now my goal is to distinguish them, right? So what am I going to do? Well, here there really are 2 cases, right? Their case I could be small, I is not equal to J. So there's 2 cases, either I is less than J or J is less than I, right? And what we often say in math, we say without loss of generality, I'm going to assume that I is less than J, right? Why do I assume one's less than the other? As well, because if it was the other way around, we just swap I and J, alpha and J and beta, right? Because right now there's nothing that's he could have given us alpha and beta or about beta and alpha. There's no difference, right? So we could prove the one case where I is less than J, and we can prove another case where J is less than I, but the proofs would look exactly the same, right? Just swapping alpha and beta. So I'm saying, let's just assume it's the one way, all right? So alpha is the small one and beta is the big one, right? So So what do I want to do? I want to come up with, when do we say no? We say yes when the second, the number of ones is smaller, and we say no when it's bigger, right? So here, I'm going to make zeta be either the I or the J, right? I don't know which one necessarily. Let's just try one and see if it works, right? So let's just try and make it the J, right? So now let's see, alpha zeta is going to be I zeros followed by J zeros, right? Well, J is bigger, right? So that means J is bigger. Oh, that means it's a no, right? And if now, what about if they're, what's beta zeta? Beta zeta is 0 to the J, 1 to the J. Well, now they're equal. And if they're equal, it's a yes, right? Does that make sense? And you might say, how did I know to do J here? I could have used I here, or I could have done I plus 1, or I could have done J minus 1, right? I don't know. I probably just, either I thought it through, or I tried various things until I got something to work. Right? Does that make sense? And so I won the theorem, and hence that's done. Right? Everybody got that example? All right. So I got one person here who's really nice, and he's shaking his head. I can't say his name. Dong Yi Yang Ho. Thank you. He shakes his head, and then I go on. Right? All right, so now let's do another one here. Right? What's this one? This one is a string, any string of zeros and ones, followed by any strings of A's and B's, but the number of 0 and 1s has to equal the number of A's and B's. All right? So let's see what we can do. I'm gonna guess that my first names are any string of zeros and ones, right? Does that make sense? The first name is strings of zeros and ones, so that's what I'm going to have as my set S. Are those strings all distinguished? Can I distinguish between every pair of them? No, you can't distinguish between every pair. So if that's my set, then, well, first off here, we could say the adversary, he gives me alpha. What's this? Does he give me that? No, that's not a string. That's a set of strings, right? And he doesn't give me a set of strings. He gives me 2 strings, right? So that's not good. Alpha and beta are not supposed to be sets of strings. They're supposed to be strings, all right? So when you're doing math and you're doing coding, make sure you do a type check, right? Alpha is a string, and this is a set of strings. So that's bad, all right? So don't do that. All right, so the adversary can give me any 2 strings, right? As long as they're in their strings of zeros and ones. So he's going to give me, alpha is going to be 3 zeros, and beta is going to be 3 ones, right? Are those distinguished? No, they're not distinguished, right? Because all we care about the first name is how long it is. I don't care whether they're zeros or ones. All I care is how many letters there are. And here the number of characters is the same. So any string of alphas, if I have any string of A's and B's, if I have 3 A's and B's, for both of these, it'll be a yes. And if I have a different number of A's and B's than 3, the answer will be no. But the language does not distinguish between these, right? Does that make sense? right? So we say, are these distinguished? No, they're not distinguished, right? They have the same length. So any zeta, these alpha zeta and beta zeta will have the same answer, right? Right, so my set S is way too big, right? I have way too many strings in it. So somebody tell me a better set S. What do we care about? We care about the length, right? Our intuition is that every state, when it's read the first name, what does it have to remember? It has to remember the length. Anything else about it, like which characters of that length, don't matter, right? I don't care which 3 characters there are. So I need a set S where for every length, there's only 1 string, right? So my set S will have all these lengths, but it'll only have 1 string for every length, right? So I'm going to let my set S be 0 to the n, right? I don't care about, I know the language can have 1s in it, but I'm not going to focus on that. I'm only going to focus on the set of first names being any number of zeros, right? Because those that need to be distinguished, all right? So I had to come up with the set S that are distinguished, and I know what's distinguished is the length of the strings. So I'm going to have a different length for every string in my set S, and so they might as well all be zeros, right? Again, now the adversary has to choose 2 strings from these, and these are only zeros. So he has to choose some 0 to the I and some 0 to the J, right? And then I get to choose my zeta, right? He comes up with alpha and beta. I get to choose zeta. Now, I could have my zeta have alphas and betas in it, right? But I don't need to. I get to choose my zeta however I want. And I'm going to choose my zeta to be IAs, right? Why? Because this is of length A and this is not of length, this is of length I and this is not of length I. So I'm going to have my zeta be of length I. Now I look at what's alpha zeta. Alpha zeta is 0, I zeros followed by IAs. Is that a yes of our language? Yes. What about beta zeta? It's J zeros followed by IAs, where I and J are different. So that's a no. All right, people getting this? And so we're done.
Sir, I have a question.
Yeah.
So the same way we're comparing 0 and A, can we also do the same for 1 and B?
Yeah, there are
Okay.
lots of different ways you could have done this. Lots of different ways. S should have, for every length, there should be 1 string. So for every length, you could pick an arbitrary 0, 1 string. It wouldn't have mattered. Right? You just can't have an S 2 strings with the same length. And this was a nice way for me to make it so that I didn't have 2 strings with the same length. Right? And then when I chose, then it exists, the zeta doesn't exist. So I get to choose, right? The alpha, the for all here, right? He has to choose zeros. Why? Because he has to choose things from my S. And my S only has zeros, right? So he's restricted to choose zeros. And then I get to choose zeta, and I could choose my zeta to be A's or B's or C, not C's, right? And I choose it, well, what matters is the length. So I'm going to focus on A's. Everybody get that? Should we do one more?
Yeah.
Okay, here's one more. Now it's the number of zeros followed by the number of ones, where the number of zeros is greater or equal to 100, and the number of ones is less than or equal to 100, right? So I'll do the same as I did before. Maybe I'll let any number of zeros, right? And then he gives me a number, 2 strings, alpha and beta, right? Oh, and here I'm gonna have all my strings be greater than 100, right? I decided that. Then I have to come up with some zeta, right? So if I make zeta be 100 ones, right? Well, I know the first names are all greater than 100, right? So the second name, if the second name is less than or equal to a number, to 100, we get all yeses, right? That's not working. Let's try something, right? You can try various things, right? You can try various proofs here, and none of your proofs will work. And why will none of your proofs work? Is because actually a DFA can solve this, right? What's my DFA going to do? Well, L1 just says, hey, do I have at least 100 zeros, right? You count them. I count up to 100. I use 100 states to count up to 100 and make sure I have at least 100 zeros, right? And then I count the ones. I count up to 100 to make sure I don't have more than 100 zeros, right? And then I know the answer. So this can be done by a DFA, and that's why I proof failed. And here's just some write-up of it. Any questions?